Thank you very much for the introduction. It's an extreme honor to be here and recognized for my contributions. Thank you to the Nagamori Foundation and Mr. Nagamori, and congratulations to my colleagues. I'll talk today about our contributions in hybrid exoskeletons and shared control systems for rehabilitation. Robots are ubiquitous in manufacturing scenarios, such as this automotive assembly line. Here you see large, geared robots performing precise and repeatable movements in a highly structured environment that's free of humans. But robots designed for human environments must take a different approach. Here, we have a personal assistant robot, a rehabilitation robot, and a surgical robot. In all of these cases, the environments are human environments. They're cluttered, they can be unstructured, and we all know human behavior can be quite unpredictable. So we must take a different approach when designing robots for these kinds of environments. Since 2003, my research group has been designing novel robotic exoskeletons for upper extremity rehabilitation and movement assistance. Our robotic devices exhibit low inertia, zero backlash, and high force bandwidth. They're also back-drivable, meaning that you can move them freely when they're unpowered. This approach to the design of our robotic exoskeletons means that we can implement advanced impedance control algorithms that are well-suited to human-robot interaction applications. My research has two primary contributions that I'll describe today. Again, we're focused on applications of rehabilitation and movement assistance for individuals who've suffered a stroke or a spinal cord injury. Our first contribution is the development of minimal assist-as-needed control algorithms that promote active engagement in therapy by modeling the contribution of the human in real time and adapting to their changing capabilities throughout rehabilitation. And second, for people who are fully paralyzed, we've developed hybrid control algorithms that combine the effort of an exoskeleton with electrical stimulation of the user's own muscles to realize movements that assist them in activities of daily living. And we're the first group to demonstrate these complex multi-joint movements in the upper limb, particularly with the spinal cord injury population. So, individuals who suffer a neurological injury like stroke or spinal cord injury experience a loss of upper limb movement coordination. They require extensive rehabilitation, and despite rehabilitation, often continue to rely on caregivers to perform daily tasks like feeding or grooming. Our vision is to develop robotic systems for neurorehabilitation that can restore their motor coordination or assist with their movements so that they can return to an independent lifestyle that they had before their neurological injury. So I'll dive now into a little more details on our two contributions. First, for applications of robotic rehabilitation, we know that it is essential that our patients be maximally engaged in their rehabilitation therapy, both cognitively and physically. So we need a robot that can learn to work with a human and adapt to their changing capabilities throughout the course of their rehabilitation. We've developed a minimal assist-as-needed controller. This is an adaptive control algorithm where we, in real time, model the capability of the user by comparing the trajectories that the robot follows with what's expected and attributing errors from the trajectory to changes in the user's capability to contribute to movement. In this approach, the robot assists only as needed to complete the movements and vary the challenge of the task to keep the user engaged. In this video, you can see our minimal assist-as-needed controller in action. At first, our participant is passive, allowing the robot to carry the limb through the range of motion fully. But as they go out through the course of their therapy, they regain some motor coordination and they're able to start leading the movement. In this case, our minimal assist-as-needed control algorithm will detect changes in the system behavior and attribute those changes to improvements in the user's capability. As such, it will reduce the assistance provided by the robot and allow the user to lead the movement and carry out the rehabilitation. This algorithm was developed with my former students, Utku Palavan and Dylan Losi, and it makes no assumptions about user capabilities, about movement patterns, or workspace limitations of the user. It's fully adapting in real time to changes in their capability, keeping them engaged in their therapy exercises. We're also moving these technologies from the lab to the clinic and the home. After his graduation, Utku Palavan started a has a startup company called Houston Bionics, where he's taken the technologies from his PhD and he's developing these upper limb rehabilitation robots that can be used in the home to facilitate rehabilitation following stroke. And two medical device companies, Harmonic Bionics from Austin, Texas, and Barrett Medical, are using assist-as-needed control algorithms in their commercially available robots. Our second primary contribution is for individuals who are fully paralyzed after a spinal cord injury, who will not benefit from rehabilitation, but still need assistance with movements for everyday activities. In this case, we are reanimating their paralyzed limbs by using a hybrid system that combines our exoskeleton devices with electrical stimulation of the user's own muscles to generate movements. In this case, in our hybrid system, our neuromodulation is achieved through functional electrical stimulation. This is where we do prescribed electrical stimulations to electrodes placed on the arm. These systems are lightweight, low cost, and have very low power requirements. However, the movements that result from this stimulation, because it is a feed-forward model-based system, are often inaccurate and don't have enough torque output to overcome gravity. Exoskeletons, on the other hand, enable precise and repeatable movements of the upper limb, and they can carry complex trajectories in multi-degrees of freedom. Their large size and power requirements, however, limit exoskeletons to clinical settings. When we combine the two, we realize the advantages of each and overcome their limitations. Our combined exoskeleton functional electrical stimulation system requires lower power to operate than using an exoskeleton alone to assist movements. And when we couple the exoskeleton with electrical stimulation, we have movements that have a greater accuracy and generalization compared to FES alone, using the onboard sensors of the exoskeleton to implement closed-loop control algorithms. Our model predictive control approach for this hybrid neuromodulation system combines the exoskeleton assistance with muscle stimulation, optimizing power use and ensuring smooth and efficient limb movements. And we validated this in elbow and wrist trajectories. Our approach combines 3 inputs on 1 degree of freedom, here shown as the elbow. We have the exoskeleton assistance, which is the torque commanded to the motor, actuating the elbow flexion extension joint of our robot. And we have 2 stimulation parameters, alpha 1 and alpha 2, that are the stimulation parameters for the biceps and triceps muscles. Model predictive control uses estimates of future behavior of the system to optimize the inputs to minimize the power consumption of the exoskeleton and ensure smooth movements of the hybrid system. Our algorithm defines a cost function J, where we compute the input vector U to balance several competing objectives. We aim to move the arm accurately along functional trajectories, like raising a cup to the mouth. We also want to preference the use of electrical stimulation over the exoskeleton, and we want to react smoothly despite the inherent time delays of electrical stimulation so that we have functional movements in the end. Here's a video of the hybrid system implemented in an able-bodied user. You see the robot moving through a 4 degree of freedom movement with 8 electrical stimulation locations on the arm. The user is not doing anything volitionally. The movements are a result of stimulating the muscles in a prescribed way in combination with torque commands to the exoskeleton. You can see the time series plot of those stimulations to each of the 8 electrodes scrolling across the screen. Our hybrid system uses less power than an exoskeleton alone to achieve these same complex movements with tolerable errors for functional tasks. And we're the first to demonstrate this in multi-degree of freedom movements. We're also translating this work to a clinical population. Garrett, shown in this video, suffered a spinal cord injury and is unable to move his limb through the movements you see here on his own. But with our hybrid system, we can stimulate his muscles, which still respond to electrical stimulation and contract, couple this with our exoskeleton so that he's able to realize these complex movements that he can then do independently. Garrett said it felt, when he used our system, like he was doing the work himself because it was the stimulation of his own muscles contributing to the movements. These advances in robotic exoskeletons and control algorithms for rehabilitation and movement assistance move us closer to our vision of portable, personalized neurorehabilitation. We see a future of wearable devices that adapt in real time to users' changing capabilities, restoring their independence and autonomy, empowering recovery through intelligent control. I'd like to thank all of my current and former students who've contributed to this work, our collaborators, of course, our funding agencies, and most of all, I want to thank the Nagamori Foundation for the recognition in this award. Thank you.